So here we're going to look at linear functions and their applications. So when we have a linear function, and we are referring to it now as a cost function, it's the cost of producing a certain number of items, and it is linear no matter how many items are produced. And therefore we write it as c of x equals mx plus b. And this is the same as a slope-intercept equation that you're used to, where m in this case, instead of calling it slope, we're going to call it the marginal cost. And this is the rate of change of cost at the level production of however many items. And this is also referred to as a slope. It's referred to also as a rate of change. It's also defined as the increase and decrease in cost for the next additional items. So if we know the cost of a certain number of items, let's say 100, then it approximates the cost of the next item, the 101st item. And B is your fixed cost. So this is usually an upfront cost or some sort of fixed cost that we know from month to month, such as rent or electricity or whatever, things of that nature. Our revenue function is from selling a certain number of units. So this is how much money we make when we sell a certain number of units. And so this is referred to as R of X equals P times X. So price times number of items equals our revenue. And this is the money that we're going to make. All right. Our break even is when our revenue equals the amount of the cost. So is the amount we're making equal to the amount we're spending to make the items? That's our break even quantity. Our break even point is our ordered pair, or break even quantity X. Okay, so whatever X items we make, that's our break even quantity. Profit is the difference between the revenue and the cost. So if we subtract what we make minus what it costs to make the item, that's how much profit that we're going to make for that particular item. And that's P of X, referred to as P of X, so R of X minus C of X, so revenue minus cost equals our profit. Right? So the first thing we want to do is we want to write some linear cost functions. So here we have a Lake Tahoe resort, charges a snowboard rental fee of $10 plus $2.25 per hour, where $10 here represents a fixed cost. It doesn't, no matter, even if we rent the board, 5 minutes later we bring it back, we're still going to pay $10. And then $2.25 per hour is just how long we have the board out. So if we were out for the whole day, 8 hours, this is how much we're going to pay per those 8 hours. So our cost function here is going to be $2.25 times the time that we're out, the hour, plus the $10 rental fee that we had to pay up front. Right? Here we have a parking garage, $2 plus 75 cents per half hour. All right. Here we have to notate that X is a half hour, not an hour, unlike the previous question. And here we have 75 cents times our half hour and our $2 that they're going to charge us regardless. Okay. We have to remember in this case, if we're asked what X represents, we have to remember that that's every half hour. So if X was 4, that's actually only 2 hours. All right. Here we're going to go ahead and look at linear cost functions. And if we have a fixed cost of $100 and 50 items cost $1,600 to produce, we can go ahead and find our slope from this. So from here, we actually have 2 points. 0 and 100 represents our fixed cost. If we don't do anything, we still have a fixed cost of $100 that we have to pay regardless. And if we make 50 items, it costs us $1,600. So from here, we can go ahead and find our rate of change, our slope, and it is 30. And then from there, we could say, okay, our cost function is our slope, 30x per item, plus our $100 fixed cost. So our slope times number of items plus our fixed cost. All right. Our marginal cost, $75. 50 items cost $4,300 to produce. We have a slope, but we do not, at this point, unlike the other one, we do not have our slope. So we have to find it, okay? We have our slope, but we don't have our other item. So in this case, we have to go ahead and use our point slope function. So a marginal cost is our slope. We're going to go ahead and use this equation to go ahead and plug in our items. So we have a 50 items, which would be our X, 4,300, which would represent our Y. Plug it into our point slope function, and we get a cost function of 75X plus 550, where the 75 should match our slope that we were given for our marginal cost. Okay. So t-shirts, if we're going to go ahead and sell some t-shirts, she has a marginal cost to produce a t-shirt is $3.50. This would represent our slope. And her total cost for 60 t-shirts is $300. And she sells them for $9 each. That's pretty decent. And so what we want to do is we want to find the cost for her production. And so our cost function here will be $3.50. And going ahead and plugging it into our point slope form, we get the 90 for our intercept. Okay. And you always want to make sure you double check this result, because this will oftentimes make a difference for multiple questions that are going to be asked after you get this equation. So we want to know how many t-shirts she must produce and sell in order to break even. Remember, our revenue equals our cost is our break even. So our revenue is $9 per t-shirt. So she sells them for $9 each. We're going to set each of these equations equal to each other. So 9x is equal to $3.50 x plus 90. And we'll go ahead and solve $16.36. Okay. This is not a money amount, even though it looks like it. X is 17 t-shirts. This represents the number of t-shirts she must produce to break even. So she must sell up one more to break even, because if she only sells 16 t-shirts, then she will not completely break even. She's actually losing a little bit of money. So she must sell 17 t-shirts in order to go ahead and break even. And now we want to know how many t-shirts she must produce to make a profit of $500. Remember, our profit is revenue minus cost. And so when we go ahead and take our revenue, 9x minus our cost function, and we go ahead and set that equal to $500, we get 108 t-shirts. So in order to get $500, she has to sell 108 t-shirts, because remember this 107, we have to go ahead and round that number up. Here we got a cost function given to us from a firm that has production costs. We also have a revenue function that is given to us. And we also know that we can't have more than 59 units sold. And so I want to find a break-even quantity and then find the profit. All right, so this is a slightly different question. So first of all, we want to go ahead and find our break-even point. So we want to set our cost function, which is given, our revenue function that's given, set them equal to each other. All right, and we end up with 60 units being sold. So this is our break-even point. Okay, so 60 is outside of how many we are allowed to sell. We're only allowed to sell a maximum of 59. Okay, so we're not going to make a profit on this. If we can only sell 59 items a day, our break even is 60, we are never ever going to go ahead and make a profit on this product. All right. If we want to go ahead and find that, we could go ahead and get our profit equation. But again, we're not going to make a profit. We are going to lose money with this particular product. All right. So when we're talking supply and demand, our Q is the quantity produced or sold. So this is the number of things we're producing and selling. And P is our price per unit, like our t-shirts that we sold for $9 each. And our demand is based on the fact that we want that demand decreases as a price actually increases. So as a price of an item goes up, the demand for that item goes down. And we want to think about that also. You know, our supply increases as the price increases. So if the price of an item goes up, people are less likely to buy it. But let's say that item goes on sale. All right, then we're more willing to buy that item. So what would happen is we know that if they're making more money and producing it and selling it at a higher, they're willing to produce more, but the consumer is not willing to buy as many. All right, and so we're going to use Q as our independent variable, so like our X value, and P is our dependent value, our Y value. So the quantity depends on how many things we are selling. All right. And so we're going to see these written as P will be as DQ, and P will be as SQ, where D is demand, S is supply. All right. Let's go ahead and look at sort of a graph here. And so here we have demand. So as our price decreases or increases, the demand goes down. So where they meet is actually our equilibrium point. That's where everybody is happy, where the producer is making a profit and the consumer feels like they're getting a good deal. Okay. If the price is too low, they're willing to supply less, and so there's a shortage. When the price goes up, the consumer buys less, and therefore there is some sort of surplus going on. All right. And we really want that happy spot for everybody where our demand meets our supply. That means that whatever I'm producing, it is going ahead and getting sold at the price that I'm asking for. Okay. Our surplus, if our demand is less than our supply, and our shortage if our demand is greater than our supply. Okay. So let's go ahead and look at a problem here. So suppose the demand and price for a certain model of wristwatch is by this formula. P is the price in dollars, and Q is the quantity demanded in hundreds. This is important. You always need to know what units you're working with. And I want to find the price when the demand is 0 watches. All right. Well, if I'm not selling any watches, the price is going to be $16. This whole piece disappears, and all I'm left with is the 16. Okay. What about when the demand is 400 watches? Now remember, our demand is in hundreds. So even though we have the number 400 here, we actually only want to plug in the number 4. Because the quantity is in hundreds. All right. And when we go ahead and plug in 4 into our demand equation, we get $11. All right. So when 400 watches are demanded, the cost is $11. All right. We want to find the quantity now for when the price is $6. So now in this case, we want to go ahead and set our equation equal to 6 because that's the price. And we're going to find the quantity is 8. So 8 watches? No, that's 800 watches for when the price is $6. So there's a lot more watches demanded when the price goes down to $6. Okay. Suppose the price and quantity of the watch are related by this equation. All right. Now I want to find the quantity at $0. Okay. So when I ask for nothing, okay, 0 watches. Okay. The quantity supplied at $20, we get 26.6700. All right. So that's actually, we got to translate that. So when we have this decimal number, multiply it by 100, and we get 2,667 watches. Okay. Now we want to find the equilibrium quantity and price. So we're going to set those two equal to each other. And we end up with 8. So remember, 8 is in hundreds. So the equilibrium quantity is 800 watches, which is a good amount. And it matches up here with our